Okay. So, how many of you have internet at home? So, cable modem, DSL, how many of you have cable modems? How many of you have DSL? How many of you don't know? What's the speed of your internet? Hmm? 200 what? Megabits? Okay. Anybody have faster internet than that? What does 200 megabits mean? What does that translate to? How fast can you download things with 200 megabit? 20 megabytes per second? All right, so he's claiming he has 200 megabit per second internet. I'm going to create a chart here. All technology folks should be familiar with these terms. So we know what a bit is, right? A 0 or a 1. What's a byte? 8 of those bits. Okay, so a byte is 8 bits. All right. What's a kilobit? How many bits in 1 kilobit? 1024. 1024 bits in 1 kilobit. How many kilobits in 1 megabit? 1024 kilobits. Small b. Gigabit. How many megabits in 1 gigabit? 1024 megabits. Why is it 1024, not 1000? 1024 is a power of 2. 0 and 1, base 2. All of our numbers in computing are going to be powers of 2. All right, so these are the number of bits that are in there. Now, just to keep the two columns equal, we're going to say terabit, even though nobody says terabits yet. That's going to be 1024 gigabits. For over here on the bytes side of thing, we have a kilobyte, big B. That is 1024 bytes. We have a megabyte, big B. That's 1024 kilobytes. We have a gigabyte, big B. That's 1024 megabytes. And we have a terabyte, big B. That's 1024 gigabytes. Make sense? So to get from this column to this column, we have a multiple of 8. And then there's multiples of 1024 going up and down in either column. So when he says he has 200 megabit per second internet, he's over on this side of things. So if you want to get this in terms of bytes, you divide 200 by 8. So we're at 25 megabytes per second maximum download speed. Make sense? All right. So now when you're downloading stuff off the internet, and let me just throw another example out here. So we have the common fast internet today. So 200 megabits per second is kind of your baseline. Hey, I want internet at my house from like Time Warner Cable or Spectrum. It used to be 100 megabits per second. Now 200 is their baseline. The fast internet you can buy for your house these days from some providers is gigabit internet, right? So 1 gigabit per second. internet, which is equal to 1,024 megabits per second internet, which is 128 megabytes per second internet, right? These are all the same number. That makes sense? Different ways of representing the exact same value. All right, so we're going to spend our next little bit talking about this and also number bases. All right, so because the way we represent data sizes is important to programmers. Again, we're building things on top of a strong foundation. Even though Python doesn't necessarily make us pay a whole lot of attention to data sizes, it just works. It just figures it out. Data sizes are still there. They're still important. And when you translate that knowledge to another language and things start acting a certain way, you might start asking some questions as to why. Okay. So your 200 megabit per second internet, have you ever, do you commonly download stuff and get less than 25 megabytes per second download speed? All the time, right? Why? You're paying for 25 megabytes per second.
Yeah, that only gets like 60.
You're only getting, so you're only getting 60 megabits per second?
Yeah.
So 60 divided by 8, so you're getting 7.5 megabytes per second?
Yeah,
Okay. But you're paying for 200. So you calling them up complaining?
No.
Why? He falls out of chairs, you just take it, right?
Yeah.
Just accept.
Sometimes you just have to let it go. Let it be.
So you don't think there's a better reason why you're not getting the the download speed you're paying for? Anybody else have internet and they don't get the download speed that they're paying for? Why? All right.
Depends on the time of day.
Okay, could be the time of day. So certainly here on campus, that could be a contributing thing, right? In the middle of the day when everybody's using the network, sometimes you might have congestion, things are slower, where you're not even able to get out to the source. Okay, we're still not on the answer yet though. So when you have 200 megabits per second, typically this is probably 200 megabits per second down by, I'm just going to make something up. I'm going to guess that you probably are at, you think 50? 50 megabits per second up? 15? That would be a weird number. Go with 16 megabits up, power 2. All right, so bottom line is that your download speed is much faster than your upload speed for consumer internet. This is called an asynchronous connection, as opposed to business internet, like the university here would have synchronous internet connections where our bandwidth is the same speed up and down. Okay, so this is kind of where things are, where I'm going here, is when you are trying to download something at 200 megabits per second, theoretical maximum, that's what you're theoretically capable of getting. You are at the mercy of how fast the person who's giving you that data can give it to you. You're at the mercy of their upload speed. So let's say I'm serving the file you're downloading. You're probably something, like Backstreet Boys or something like that, MP3. Okay, and I'm serving it off of my dial-up modem, which can upload at roughly 3K a second, let's say. The fastest you're going to download from me is 3K a second. Because I can only push it out at 3K a second. Even if you could take it at 200 megabits per second, I'm only pushing it out at that. Okay? Think of the internet, think of your bandwidth as kind of like the water coming to your house. Okay, you might have this huge pressure of water coming to your house, but it's only going to come out of the faucet so fast. The faucet has a restriction and things like that, but if you turned all the faucets on in your house, Do you think you're going to have a drop in water pressure? How many of you have ever been in a shower and somebody else flushes a toilet and all of a sudden you have this drop in water pressure or something like that? Okay, because the water that was coming to your house, the amount you were downloading, right, coming into your house, could not be maximized across all of your uses in the house. So you lost some of your pressure. You dropped from 200 megabits per second down to something less. All right, so when you're downloading from a place, you're at the mercy of what's the fastest they can push it to me. And remember, their upload speed also has to be divided among all the other people that are also downloading from them. So if I can upload at 5 megabits per second, and I have 5 people downloading from me, and they all have faster than 5 megabits per second, let's say, each of them is going to get 1, presumably, right? So I'm dividing up my bandwidth among all the people that want it. This is why technologies like BitTorrent work. How many of you have heard of BitTorrent? Okay, you've seen torrent files, .torrent files. Now, commonly these are used for not so great reasons, but it's not an illegal technology, and many legitimate service providers use BitTorrent to distribute their software updates. Microsoft does, Blizzard for their World of Warcraft games, things like that. Because you think about the number, how many people in the world are running Microsoft Windows? Round down and call it a lot. Okay, how many people are playing? Pick your favorite video game that sometimes releases software patches. A lot, less than are running Windows, but still a lot. All right, so if they have to release a software patch for Windows or a software patch for your video game, and you have a lot of people all trying to get that at the same time, I don't care if it is Microsoft, who we presume has a pretty solid internet connection. If they can only pump it out at some ridiculous number, but now you're dividing that ridiculous number by an even more ridiculous number of users who all want it at once, you're not going to be able to get that very quickly, are you? So historically, what was the solution? They staggered the release, right? They would kind of, a certain percentage of people would get it. It would start coming over like a 2-week period where some people would get the updates, other people wouldn't. Now they do the same thing, but they actually do it across a BitTorrent type technology. So as people start getting the updates, they also become providers for other people to get the updates from them. So what BitTorrent does is it creates a network of people all with the same file. Let's say we all have the same 5 megabyte file. And, except you want the 5 megabyte file. The rest of us all have the 5 megabyte file. But let's say that you have some crazy download speed, and all of our upload speeds are not as good as that, okay? You'll download some of the file from me, and at the same time, you'll download some of the file from him. At the same time, you'll download some of the file from her. So we're each serving you a portion of the bits in that file, right? Portion of the zeros and ones in that file. So you might maximize my 5 megabits, his 5 megabytes, his 5 megabytes, and maybe over time you will build up to your maximum internet speed because you're downloading it from a whole bunch of different sources. So if you've ever used BitTorrent and you were grabbing it from a source that had lots of seeds, lots of people who were seeding the file, that's when you get close to your maximum download speed, right? Okay, it's because you're not downloading it from one source. You're downloading it from a whole bunch of sources, and across all of them, they're able to stream bits to you up to your download speed. Make sense how BitTorrent works? The purpose of it? So why then? Anybody in here have faster internet than 200 megabits per second? That was what was cheapest? That's what you bought? Oh, you have lower? Yeah. I didn't know they sold lower. Is it from?
Not here.
Oh, okay, yeah. Here, if you do a cable modem, the slowest you can get is 200 megabits here in town. If you do DSL, which would be through the phone company, through AT&T, you can get slower. I think you could probably get 3 megabits per second would be the slowest, because the fastest DSL is like 24 megabits per second. DSL is a whole different technology. Yeah, they have it's capped. The new stuff is going to move towards like downtown Milwaukee. AT&T offers fiber, so instead of it being telephone based, POTS based, plain old telephone service, which DSL has that limitation of what can you do across copper wires. AT&T has their fiber downtown Milwaukee, which you can get up to a gigabit, and they'll probably be moving it to Mequon here relatively soon. But regardless of who the provider is, in your networking class, hopefully they talk about the difference between cable modems and DSL. What's this?
Run like fibers here or what?
Well, the fiber would be the cable, the type of cable, but given the fact that AT&T has run fiber to the buildings, that it can support their internet across, they're no longer limited by the copper telephone lines. It's called the POTS network, plain old telephone service is what POTS stands for. So this is like more of a networking class concept. But the limitation of DSL is not that it's a crappy technology. It's that it's a technology built on top of a very, very, very old technology, not unlike like our RESTful APIs built on top of HTTP. So DSL is, I would never, for instance, at my house, we used to have our cable TV through AT&T Uverse, but I would get my internet still through Spectrum, because I'm not going to deal with the maximum slow speed of DSL when you can get the budget pleaser cable modem that's 10 times faster than the fastest DSL. Now, if you can get gigabit internet at your house, would you? Well, you can get gigabit with Spectrum anywhere in Ozaki County, anywhere in Milwaukee. You can get gigabit.
That's like 200.
Yeah, it's more money. Yeah. So it is a cost thing. But you're telling me you're not even getting use out of your 200 megabits all the time, right? But I just told you how you could, right? With BitTorrents. BitTorrents would let you, if you needed to get a legitimate file, not a ripped video game or a movie or something like that, but a legitimate file, BitTorrent would allow you to come much closer to maximizing your network speed, your internet connection speed. But do you think that it's going to be even more unlikely to maximize a gigabit per second internet connection speed than your 200 megabits per second? Yeah. So why do people get it? What's the advantage of having that higher bandwidth? More simultaneous uses. What do we use our internet bandwidth for at our house? Netflix streaming, checking your email, stuff like that, playing video games, your Amazon Echo, your smart fridge, your smart toaster, your smart watch, smartphone, all these other smart devices that are in your house. In our house, my wife's all into the smart light bulbs. And we've had it for years now. So at first she had Post-it notes over all the light switches. These were training wheels, because you don't want to turn the light switch off because you have to talk to Alexa to turn the lights off. And if you turn the switch off, Alexa will no longer be able to control it. The switch has to be on, then Alexa turns the bulb off. Now she had me 3D print her things that go over the switches, so you physically can't get to them. You can kind of like snake your finger behind it and get to it. So it's like meant to, like in an emergency you can. But we haven't used light switches in our house in years. I don't even get the point. Like, what was wrong with switches? I get up in the middle of the night, she's still asleep. I have to like whisper to Alexa to like light my way. It's like, Alexa, turn the foyer lights on. And then sometimes Alexa doesn't hear me. It's like, I'm sorry, what did you say? And she wakes her up, and this was your idea. But as we think about, as families are, relatively big, you might have, 2 kids at home, something like that. So you got 2 people watching Netflix at the same time, one person playing a video game, somebody else making a video call to grandma, whatever it is. All these things add up to bandwidth usage from a whole bunch of different sources that might start pushing you towards your gigabyte or gigabit per second network connection, right? No different than your water supply, right? If you have 3 people who might be simultaneously taking a shower at your house, you probably want to make sure you have a really solid water supply coming to the house and a really big hot water heater, right? Otherwise, some people are going to be taking cold showers. Right, so it's no different than that. We're talking about the maximum bandwidth and how is it shared amongst multiple people. Now, from our perspective in here, we care about this chart. We want to know what speeds mean. We want to know how bits flow. Okay, because we might be talking about a kilobyte of data, and we want to know what does that mean for something to be a kilobyte of data. Because these terms get thrown around all the time. You watch commercials for internet. They don't say megabits per second. They usually call, it's 200 meg internet. Hoping that you've heard of megabytes or something like that, and thinking that you think your internet connection is faster than it actually is, right? They're hoping that somebody who bought the 200 meg internet thinks they're getting 200 megabytes per second, when they're actually only getting 25 megabytes per second maximum. Does that make sense? Same thing, you get the gig internet. They don't even put the 1 in front of it because 1 doesn't seem small. You get the gig internet. They're hoping it's gigabyte. No, they could give you some fraction of a terabit internet. So 1,024 megabits is so 1,024 megabits divided by 8 gets you megabytes. Divided by 1,024 gets you 0.125 gigabyte internet. Divided by 1,024 gets you 0.00012 terabyte per second internet. That wouldn't look cool, is it? So you have 200 megabit per second internet at your house, right? 200 megabit. Divide by 8 gets you to bytes. So now we're at 200. Now we're at 25 megabyte per second. Now, if you want to know that in gigabytes, we got to go down the chart, so we'll divide by 1,024. So your internet is actually 0.024 gigabyte per second internet. That's how fast that doesn't sound impressive, does it? No, it's worse. Now, if you multiply it by 1,024, now you're at 25,600 kilobyte per second internet. That's more like it. It is kind of surprising why they didn't take your 200 and multiply it by 1,024 and say it's 204,800 kilobit per second internet. How many of you ever had dial-up modems? What was the maximum speed of a dial-up modem? It was 56K, right? 56 kilobits per second. So if you're really measuring your 200 megabit per second relatively inexpensive internet at home to a dial-up modem, and we're using the same measuring factor, dial-up modems were 56 kilobit per second down. This is 204,800 kilobit per second down. Yours is way faster. So we divide that by 56. You are 3,657 times faster than a dial-up modem. It's pretty solid. But see, we're doing all this math with these numbers. As computer scientists, we need to really, really, really understand what all this stuff means. And big B's and little b's mean something. Okay? Is everybody cool with this conversion chart? All right, so let's talk about bits for a little bit. What's binary? Okay, zeros and ones. Binary really is the base 2 number system, right? So actually, let me do it like this. Number systems. So we have binary, And that guy is the base 2 number system. What's our number system? Base 10. So ours is called decimal, right? All right. What other numbering systems do computers use? Hexadecimal. We talked about that earlier, right? So we have hex, which is base 16 number system. Any other base that computers commonly use? Octal, which is the base 8 number system. So how many of you are can write numbers in binary? Like if I told you to write the number 21,604 in binary, could you do it? Okay. Okay, what about octal? What about hex? Just great confidence flowing around here, right? Let's talk about numbering systems. But we're all comfortable with decimal. Base 10, 10 fingers, 10 toes. We're good with that? Okay, we've been doing that for a while. Unfortunately, computers, they're not cool with decimal. They need it ultimately in zeros and ones, and they will they will partially represent stuff in base 8 and base 16, and we'll talk about why here in the next little bit, why they've chosen those specific ones. Is there a such thing as like a base 3 number system? No?
I don't know.
What about base 4? Base 5? Base 13? Do they exist? So we're going to take the number 1,304 decimal. What does this number mean? We got to go back in time. This goes back to, I said human beings are so good at solving problems, we've forgotten how to articulate how we solve them. Break down 1,304 for me. What does this mean? Probably got to crawl into your first grade self. Maybe even before. I'm sure it's before that. Kindergarten self, preschool self. When did you start like doing some counting? Kindergarten? No, you just made that up. What does this number mean? What's the 4? 4 ones. So we have 4 ones. What's the 0? We have 0 tens. What's the 3? 3 100s. What's the 1? We have 1 1000s. So 1304, this is the ones place. Times 10, the tens place. Times 10, the 100s place. Times 10, the 1000s place. If I had another number in front of it, times 10, the 10,000s place. So as we move, we multiply by the base. So if I wanted to take the number 1304, convert to decimal. 1304 in decimal, convert that to decimal. We might say that doesn't make sense, but I'm going to say we have a 1 times 1,000 plus a 3 times 100 plus a 0 times 10 plus a 4 times 1. And that is 1,304. So 4's place, so 4 times a 1 plus 0 times a 10, because we're in the tens place, plus 3 times 100, because we're in the hundredths place, times, or plus 1 times 1,000, because it's the thousands place. Make sense? For a base 10 number. One zero one 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 zero, binary to decimal. This is the ones place. What place is this guy?
This is the
Why did I multiply by 10 here? This is the ones place, times 10 is the tens place, times 10 is the hundreds place, times 10 is the thousands place. Why did I multiply by 10? So we're dealing with base 10. So what do you think I multiply here when I'm dealing with base 2? So this is the ones place, times 2 is the twos place, times 2 is the fours, 8s, 16s, 32s. So this is 0 times 1 plus 1 times 2 plus 1 times 4 plus 1 times 8 plus 0 times 16 plus 1 times 32. So that is 46. This binary representation is the decimal number 46. Didn't we use the identical pattern to what we just did to make this binary number, this base 2 number, turn into a decimal number? Same thing I did here to make this base 10 number turn into a base 10 number. Somewhat of a waste of time, but it was the same pattern. What if I did this? (137) octal to decimal. First of all, what are the legal values? They're called octets in octal. What are the legal digits in decimal? What numbers do we have to work with when we make up our decimal numbers? 0 through 9. So 0 to the base minus 1. So base 10, it's 0 to 9. Base 2, it's 0 to 1. Base 8, it's 0 to 7. Base 2, we allow zeros and ones, right? For binary, zeros and ones are what we allow in our, those are the bits in the binary numbering system, zeros and ones. In octal, the octets are 0 to 7. That is 0 to the base minus 1. In decimal, the digits are 0 to 9. 0 to the base minus 1. In hexadecimal, what are the legal hextets? Okay, so it's 0 to 15 are the legal values, right? But it's 0 to 9 and then A through F for the alphabet, right? Which means that we can support bases up to base 37. Base 36, base 36. That's 0 to 9 followed by the entire alphabet, A through Z. And then if you really wanted to represent bigger numbers, you can switch over to Klingon or something like that and just start tacking on extra values. But that's how we represent these numbers. So we're going to talk about that for a while here. But we're going to say this is a legal octal number because that number contains values between 0 and 7. If I put an 8 in here, that's no longer a legal octal number because I'm using a octet 8 that is not part of the vocabulary of octal numbers. Octal numbers only allow 0 through 7s. Make sense? All right, so there's an octal number, 137 in octal, and I want to convert that to decimal. Well, I do the same thing I did before. If this is the ones place, what place is this guy? Times 8 is the eights place, because we're dealing with base 8, times 8 is the 64's place. So this is 7 times 1, so the far right is always the ones place, plus 3 times 8 plus 1 times 64. So that is 95. So 137 in octal is equal to 95 in decimal. Make sense how we're doing this? The identical pattern. When we convert any base to decimal, we use this pattern. Is this a legal hexadecimal number? 137? But I thought it was an octal number. Hexadecimal is legal as long as I use 0 through 9s or A through Fs. I don't have to use all those, right? So this guy can be hex. I have to tell you specifically that he's a hexadecimal value. Otherwise, he could just as easily be anything that's base 8 or above. The largest value in here is a 7, so this guy could legitimately be a base 8 number or anything higher than a base 8 number. So I'd have to specify what he is. He's a hexadecimal value. So 137 in hex, this is the ones place, times 16 is the 16s place, times 16 is the 256 place. 16 times 16, 256 place. All right, so that means this is 7 times 1 plus 3 times 16 plus 1 times 256, which is 311, although that's oh, yeah, that's right. That's correct. So that's 311 in decimal. Make sense? Let me show you one more. My favorite hexadecimal number, BAD. All right, so again, this is the ones place, 16s place, 256 place. But now we need to do our mapping. An A is a 10. A B is an 11. A C is a 12. A D is a 13. E is a 14. F is a 15. Make sense? So this is a 13 times 1 plus a 10 times 16 plus a 11 times 256, which is 2989. 2989. So BAD in hex is equal to 2,989 in decimal. Make sense? Same pattern. I just used the identical pattern, regardless of what base I was starting with. If I was taking it to decimal, I start at the end of it, I walk towards the front of it. The end is always the ones place, and I multiply it by the base as I go to the left. Add it all up. Make sense? One, 1, 2, 2 for base 3 to decimal. Take a minute. Try to solve it. Base 3 doesn't have a name, but it's still a base. right, we'll start here at the end. This is the ones place, times 3 is the threes place, times 3 is the nines place, times 3 is the 27th place. So this is a 2 times 1 plus a 2 times 3 plus a 1 times 9 plus a 1 times 27. So that is 44. In decimal. So 1122 in base 3 is equal to 44 in decimal. So now we have the skill necessary to convert any number between base 1 and base 36 to decimal. If we were dealing with base 17, it would go to G, which is your number 16, so on and so forth. All right, questions about converting from any base to decimal. So we can now comfortably work, I mean, we have to do a little math, right? But we can now comfortably work with that one pattern to convert from any base into decimal. What about going from decimal to some other base? We had our, let's put that out here. So we had 46 here, right? So we took 101110 from binary and wanted to turn it into decimal. We got a 46 out of it. What if I want to turn this 46 back into binary? So if I have a decimal value, 46 decimal to binary. Here's the pattern for doing that. Start with my number, and I keep whittling it down. I'm using 3rd grade math here. Remember long division, where you have a remainder? So 46 divided by 2 is 23, right? Any remainder? It's 23 remainder 0. 23 divided by 2 is what? So it's 11. 11 times 2 is 22. So I have a remainder of 1. 11 divided by 2. 5. 5 times 2 is 10 with a remainder of 1. 5 divided by 2. 2. 2 times 2 is 4 with a remainder of 1. 2 divided by 2. 1. 1 times 2 is 2 with a remainder of 0. 1 divided by 2. How many times does 2 go into the number 1? 0 times. 2 does not go into the number 1. 0 times 2 is 0 with a remainder of 1. Then we know we're done when we hit a 0 here. We read our answer from bottom up. So this is 1 0 1 1 1 0. Which should match what we had here. 1 0 1 1 1 0. Make sense? So that's converting a binary number or decimal number to binary. What if I wanted to do my octal number? So 95 from decimal to octal. So I'll take 95, since I'm going to base 8, I'll divide it by 8. 95 divided by 8 is 11. 11 times 8 is 88 with a remainder of 7. 11 divided by 8. 8 goes into 11 one time. 1 times 8 is 8. We have a remainder of 3 to get us to an 11. 1 divided by 8. How many times does 8 go into 1? 0 times. 0 times 8 is 0 with a remainder of 1. We know we're done because we ended with a 0 here. Read it from bottom up. 1, 3, 7. That's the octal version of the decimal number 95. Identical pattern, right? You don't have to learn some strategy of going from decimal to octal or going from binary to decimal, whatever. It's the same pattern to go either direction. Similarly, we had, where's my 311 decimal to hex. Denial. And we're dividing by 16 because we're converting it to hexadecimal. So 311 divided by 16 is 19. 19 times 16 is 3. 19 times 16 is 304, so that's a remainder of 7. So 311 minus 304 is 7. 19 divided by 16. 16 goes into 19 one time with a remainder of 3. 16 to 19 is a difference of 3. 1 divided by 16. 16 goes into 1 0 times. 0 times 16 is 0 with a remainder of 1. We read it from bottom up. 1, 3, 7. That's our hexadecimal version of the decimal number 311. Same identical pattern. Right? $29.89 hex to, $29.89 decimal to hex. So 29.89 divided by 16. This is 2989, and that is 186. 186 times 16 gets us 2976. So that's a remainder of 13. 2989 minus 2976, 13. 186 divided by 16 is 11. 11 times 16 gets me 176. 186 to 176 is a remainder of 10. 11 divided by 16 is 0. 0 times 16 is 0 with a remainder of 11. We read our answer from bottom up, but first we have to convert each of these. An 11 is a B. A 10 is an A. A 13 is a D. B, A, D. Identical pattern. Make sense? All right, so at this point, if I gave you any decimal number and I told you to convert it to any other base, you'd be able to do it, right? With a few minutes. You now know that pattern. So if it's a decimal number, you want to convert it to the base, to some other base, you divide it over and over again, record the quotient, and record the remainder, right? Until you get down to a 0. Divide, 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 till we end up with a quotient of 0, and we record the remainders as we go along. reading the answer from bottom up. That's how we go from decimal to some other base. If I want to go from a base to decimal, that's the other pattern where I start at the end of the number. This is the ones place times the base is so in this case it's octal. So times 8 is the eights place, times 8 is the 64's place. Add it all up. Make sense? All right, so that's going from any base to decimal. And then we have to keep in mind that for larger bases, things above base 10, they have included in their vocabulary letters of the alphabet, A through Z potentially. But typically, the biggest base you will practically deal with is base 16, hexadecimal. All right, but if somebody says convert something to base 23, you can. You just go a little bit farther into the alphabet, and you're good to go. Okay, so everybody understand these different number bases and how we can leverage them and how we have those patterns. Okay, so then the question is, why are octal and hex popular computer bases? Binary makes sense, right? Digital logic, on, off, 0, 1. That's kind of self-explanatory, okay? But why octal and hex? Why do we arbitrarily pick base 8 and base 16 to be our popular computer bases? Common computer bases. What do you think? Some evil dictator. Lost his thumbs in the war. We're going with octal. What do you think? Any theories?
Does it have to do with, also octal would be bytes, and then that's how many.
Okay.
The bytes to have the number of.
Yeah, so you're trying to connect the 8 to the 8 bits in a byte.
Well, and just that you have the number of characters you have to have 8.
Yeah,
bits
right.
In order to represent.
Yep. Not a bad logic path to go out, but that's not it. It has to do with efficiency, optimization. What are the range of values? The range of potentially you're very loosely related to it. Let's see. You can tell me afterwards if this is what you were thinking. All right, so what are the values? What are the legal octets for a base 8 number? 0, 1, 2, 3, 4, 5, 6, 7. That's it, right? 0 to the base minus 1. All right, so we have 0, 1, 2, 3, 4, 5, 6, and 7. All right, so now we want to get the octal version of the number 7. So we're going to take the 7, we want the binary version of 7. So we have the number 7. How do we represent a 7 in binary? We can take our shortcut, right? We can say 7 divided by 2. So this is 3. 3 times 2 is 6. So we have a remainder of 1. 3 divided by 2 is 1. 1 times 2 is 2. Remainder 1. 1 divided by 2 is 0. 0 times 2 is 0 with a remainder of 1. We read our answer from bottom to top, 1, 1, 1. That's the binary version of a 7, correct? 111 is the binary version of a 7. 110 is the binary version of a 6. 1's place, 2's place, 4's place, so 4 plus 2, 6. 101, that's a 5. 011, I'm sorry, 100. Then 011, then 010, then 001, then 000. So we can represent all of the octal numbers in 3 bits each. We didn't need 3 bits to represent a 0 or a 1 or a 2, but the biggest octal value is a 7, which can be represented in 3 ones, 3 bits. Oh. Hex binary representation. I'm going to start off with, well, let's just go a little farther here. So this would be an 8, a 9, an A, a B, a C, a D, an E, and an F. F is 15, which is 1111. E is 14. So this is 1's place, 2's place, 4's place, 8. So this is 8 plus 4, which is 12, plus 2, which is 14. This is 13's. 12, 11, so 1's, 2's, 4's, 8, so it's 8, 9, 10, 11. There's a 10, 1 plus 2. There's a 9, 8 plus 1. There's an 8, just an 8. So hex numbers we can represent in 4 bits.
Would those all be zeros?
Yes, they would be, sorry. So we can represent a 0 in 4 bits, or we can represent a 0 in 3 bits. It's just anything you pad to the left of it is still, doesn't change the value of it. So all of these numbers, the biggest hexadecimal value is 4 bits. Well, okay, so far so good. That seems convenient enough, right? So what? I can represent octal numbers in 3 bits. I can represent hexadecimal numbers in 4 bits. Where does this help me? What if I wanted to represent BAD from hexadecimal to binary? Well, we might say, well, let's convert it to decimal first. Then we'll convert it from decimal to binary. We'll use both of our patterns, right? You know, so this is the what? The well, we already know, we go through, this is 13 times 1 plus 10 times 16 plus 11 times 256, and we know that's going to equal 2989, right? Then we start taking 2989 and we divide it by 2. over and over and over and over again and get a whole bunch of zeros and ones. And that's the binary version of this, right? So 2989 divided by 2, 2989 is 1494. 1494. Remainder 1. 1494 divided by 2 is 747. Remainder 0. 747 divided by 2 is 373. Remainder 1. 373 divided by 2 is 186. Remainder 1. 186 divided by 2, 93. Remainder 0. 93 divided by 2, 46. Remainder 1. 46 divided by 2 is 23. Remainder 0. 23 divided by 2 is 11. Remainder 1. 11 divided by 2 is 5. Remainder 1. 5 divided by 2 is 2. Remainder 1. 2 divided by 2 is 1. Remainder 0. And 1 divided by 2 is 0. Remainder 1. With our final answer being, reading it from bottom up, is 1011101101. Easy peasy. So I'm going to rewrite BAD as 11, 10, 13. So the value for 11 is 1, 0, 1, 1. That's 8, 9, 10, 11. That's a 10. 8, 9, 10, 11, 12. Take the spaces out. And I think you'll find that that number matches this number. Is that a little quicker, going from hex to binary by just creating the 4-bit or the nibble size groupings for each of the hextets? Since we know that all the hexadecimal hextets can be represented as a 4-bit value, which are also called nibbles, we can convert it into binary quickly by taking any hexadecimal number, splitting it into its parts, and writing the 4-bit representation for each of the hextets. That's our final value. That's what I have right here. This is an 11. This is a 10. This is a 13. Do it in 4-bit groupings, you have hexadecimal going to binary. And guess what you'll find for octal? 3-bit groupings. Same thing. Pick your favorite octal number. 127 octal to binary. We can do a 3-bit version of a 1, a 3-bit version of a 2, and the 3-bit version of a 7. That's the binary value for 127 in octal, using 3-bit groupings. This won't work for any of the numbers in between because they don't fully take up the bit space. Octal fully takes up the bit space of 3 bits. Hexadecimal fully takes up the bit space of 4 bits. The next value would be base 32, which would fully take up the bit space of 5 bits. Make sense? So our next logical jump, once if we fast forward however many years, at that point we might abandon binary because now we're starting to move towards quantum computing and looking at 3 states. So on, off, or flip for quantum states. They're called qubits, is what the name of it is. So it's possible we'll just abandon binary and move on to something else. But let's pretend like that doesn't happen as our memory in our computers gets bigger and bigger and bigger and bigger. Because think about, when do we use hex right now? Base 16 we use for representing our memory addresses, right? Where all the memory addresses in our computer are on one big long street. And rather than saying, well, that's house 14 quintillion, blah, 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 we can represent a big decimal number in a smaller footprint using hexadecimal. It's more compact. We saw that up here when we looked at 311 in decimal is 137 in hex. The hex value is a smaller value. It's compressed. This one we didn't pick up any real estate because it was still three elements long. But for big values, a hexadecimal version of the decimal value will take a smaller footprint. That's beneficial for us to store that in hexadecimal inside of a computer. So if we fast forward and we start getting way more system memory, way bigger hard drives, all that stuff, even enough for you to put your virtual machine on there. Then we might eventually have a need where hexadecimal isn't big enough. So our next logical efficient thing would be to go from a 4-bit representation for hex numbers to a 5-bit representation for 32-bit, or base 32 numbers, rather. So that'll allow us to have 2 to the 32nd power be 11111. That's not accurate. The 5-bit thing is accurate, but the 2 to the 32nd power is not 11111. So this value here, 11111, this is the ones place, the 2s, 4s, 8s, 16s. So this is 16, that's 24, 28, 30, 31. So this is 0 to 31, 32 total bits. So if we wanted to represent base 32, we can do it in, because base 32 supports the characters 0 to 31, right? 0 to 9, and then A through something late in the alphabet. Not quite to Z, but almost to Z, whatever that is. So we have 32 unique, they wouldn't be hextets, they'd be whatever the name we give to base 32. 32 vocabulary characters, and we can represent them with 5 bits. All right, so that would be our next logical jump. Rather than, we couldn't go to base 17 or base 18 or base 19 because we're only taking up part of that bit space with our 5 bits. We need to fully take up the space in order to conveniently, in order to accurately map it to binary. When we did this guy in binary here, we had to use all of the 4 bits in ones to get our maximum value. To go to 5 bits, we would have to use all of our 5 bits in ones to get our maximum value, which takes us to base 32. All right, so that's the rationale why we use octal and we use hexadecimal for our non-binary numbers in our computer. So anytime we use decimal, it's because humans are involved. And computers will often store values as decimal as well, especially when we're working with assemblers and we're seeing it. So whenever we see decimal, it's because we're involved. Whenever we see hexadecimal, it's because we need to take a really big value and have it in a smaller footprint. And hexadecimal is convenient to work with binary. Octal, also convenient to work with binary, and we use it for some things in networking for masking values and things like that. All right, questions about any of that stuff? All right, so now we have an understanding of how values are represented under the hood inside of our computer. Okay, so I'm just going to start a slide here called primitive types. All right, so let's go ahead and take about a 10-minute break, and we'll come back and we will, let's permit, I misspelled this. And we'll come back and talk about our data types in Python. So come back at 8:52, 8:55, something like that.